Thank you. First of all, I would like to thank the organizer, especially Professor Zhou, and for invitation and have an opportunity to meet many friends here and to introduce some work on algebraic integral geometry inequalities, and also something include our recent work. Let's start. Okay, mathematics is the most beautiful and most powerful creation of a human spirit. And mathematics is as old as man. So the man from beginning and born and no mathematics. Okay. Only these countries that cultivate mathematics can be strong and powerful. So this is by Barnard. And also, Clifford said geometry is a gate to science. So that's so geometry is important. This gate is so small that one can only enter it as a child. So, and we have to study geometry from very early beginning. Okay. So, and integral geometry is based on the geometric measure. So actually, if we in global differential geometry, and we have two basic concepts. That means curvature and volume. If we have the manifold and also geometric subject, what will concern first is the size. That means the volume. And the second is something about topology. That means the shape. And also the curvature. That's what the curvature. Okay, we must know. These are two basic. And some recent researches are focused on integral relate to variations of curvature and volume. Okay, so any research must be based on the curvature and volumes. These integral formula are based on the geometric measure on the set of geometric subject. For example, we investigate the sets of lines, sets of planes, sets of linear spaces in the Euclidean space, and this is also called Grassmann, and also sets of convex sets and many other things. So geometric inequality is the study of a geometric measure. If you have a geometric measure, those geometric measures called Hahn measure in a measure theory, which are integrals over the group of isometry integral geometry. And so integral geometry closely relate to convex geometry and geometric probability, and consider a part of a global differential geometry has classic root in the work of Barbier, Crafton, and Poincaré and others. Later, Blaschke, Chen, Weil, Santalo, and others make contribution to this branch of mathematics. It began with a study of invariant measure on geometric object. Those geometric objects, just like we said in previous slides, and the set of convex bodies. So those invariant measure and leads to integral identity and inequality that have a remarkable application to probability and other mathematical branches. The integral formula established in integral geometry are fundamental in those branches, and the applications in medical science, biological science, medical science, information science. And let's to describe this. So to apply the idea probability to random elements that are geometric objects, like we stress on this again and again. So those geometric objects means like points, lines, geodesic, and linear subspaces, congruent sets, motions, transformations, or affinities. It is necessary to first to define a measure for such a set of elements. Then evaluation of this measure for specific sets sometimes leads to remarkable consequence of a pure geometrical character, in which the idea probability and turns out to be excellent. The definition of such a measure depends on the geometry with which we are dealing. According to Klein and Erlangen program, the criterion that distinguish one geometry from another is a group of transformation, and which the propositions remain valid. Okay, and therefore it is natural to choose the measure in such a way that it remains invariant and the corresponding group of transformation in integral geometry. So thus those concepts such as a probability measure group and the geometry focus the basis of integral geometry. So integral geometry is also based on the measure. Those measures and must be invariant and a certain group, and also the criterion from Klein's Erlangen program. Okay, so let's start. Okay, what's called a geometric inequality? Okay, geometric inequality. A geometric inequality or equality describes the constraint on the geometric invariant, like volume, surface area, curvature, Poincare characteristic of a geometric object, domain, simplex, compact, submanifold. Okay. Okay, now we have like the, okay, this is okay, like this. Okay. All this we must to compute the volume, and also surface area, and the curvature. Okay, like the curvature of the shape, and also the Poincare characteristics. Sometimes we have many examples here. So basically, so how do we investigate? Like we give the K. Okay, this K can be the convex body, can be the simplexes, can be the submanifold. So what's the way, the integral geometer, to investigate the property of this K? So usually we take the intersection, okay, by a linear subspace, okay, to cut, okay, to intersect. And then if we know, we try to investigate the intersection, okay? We try to investigate the intersection. If we know enough for this intersection, for all directions, for all the intersections, we want to use the intersection to estimate the global K. Okay, so that's the mean. Okay, from the local to estimate the global. Okay, so this is the one by intersection. This is the integral geometry. And also, we have another way. Okay, if we have a subspace, sublinear space, we have a K, a submanifold or convex body, by projection. Okay, by projection, we don't know the whole K. If we have an intersection projection, if we know enough, how we know the information from the projection, from every direction for the intersect projection. We want to use this property and to get the information for the K. Okay. So this is another way. Okay, another way. So this is the integral geometry, and we can do something. If we have the M, if we have N, the two manifold, we want to go by motion, rigid motion. We move this K, the N, to intersect with the M. Then we investigate the intersection. Then we know, if we know enough, know many, we try to get the information. We know the information from this. Then we try to know what's happened. What's the information for N and M. So that's the integral geometry. We have three methods, three-way. Usually it's a three-way. And projection, intersection, and the moving intersection. Okay, try to use the way. And then I will explain, and hopefully if we have time, we want to do this. And usually, for geometers, and we try to say some intuition. Okay, we want to say some intuition, because geometry we want to imagine something. This is obvious, or so that is the intuition. But intuition in mathematics for geometry is dangerous. Okay, and we cannot get the clue from intuition. Okay, let's see. We use some example to say, okay, for example, intersection by a linear subspace. We take this, and so the Busemann-Petty problem. In 1956, Busemann-Petty asked the following question. Okay, suppose K and L are origin symmetric convex body, convex, and also very strong origin symmetric in Rn, such that the intersection for hyperplane passes through origin, and the intersection, the volume of intersection is less than this volume intersection. Then we will ask what happened for the global. Okay, so this is like if we have a K. Okay, if I have K, okay, symmetric, okay, this one is not symmetric, but I will say that, okay, if this is L, okay, if we have this is the H, okay, if this is also the H, okay, this is a KH. Is the incident section. So this is length, this is volume. Okay. Here this is L. This is a volume. Okay. Okay. So therefore, this is always short than this one. For any direction, we ask if this is K, the area, the volume of K is also less than this one. Okay. So imagine that this one should be true. Intuitively should be true. So this is the one in 56. Busemann-Petty put this, and this one the problem has a long and dramatic history. Okay, we said that is N for the tuition in three-dimensional, two-dimensional. That's true. Okay, so a negative answer to the problem for N greater than 4. was established for a long time. First, and for n greater than 12, Lama and Raj and give the counterexample. So that's not true, okay, for n, high dimension. And Kisbor and prove that n is bigger than 10 is not true. And then Giannopoulos and Bogan independently and prove give a negative. Say this is negative. N is greater than 10. And this work is one of the works of made by Bogan for him to won the Fields Medal in 1998. So then, and the Gardner and Papadimitric independently and said n is greater than 5. That's not true. Okay. And then later Gardner proved that the answer to the Busemann-Petty problem is affirmative when n equals 3. So intuitively it's true. For n equals 3 and for n equals 2 it's true. For n equals 2, if this length is always less than this length for every intersection, so this area is less than this area. In 3 dimensions it's true, but the negative answer in the case was claimed in 1994, but 3 years later, the main argument to the proof was shown to be wrong. Okay, so then in 1998, and by Zhang, and published a paper in the Annals, showed that the answer is affirmative when n equals 3. So for this Busemann-Petty problem, when n is greater than 5, it's completely negative. And those people, they use some Fourier theory and some analysis method, and also the Kisbor used the probability theorem to prove this. Okay, so this is just the example for how the intersection. Okay, it's the one and interesting, but it's not intuitive. So those are papers. And there is a series of these papers. Okay. Okay, so let's take another look. How about the projection to a linear subspace? Okay. And if we have the K, and we project to a plane, this plane is passes through the origin. So this is a linear subspaces, a linear subspace. So all this, if we want to project to every linear subspace, that means this is a Grassmannian, okay, in a manifold way. Okay, so we call it a supported hyperplane. Okay, for set K in Rn, if there is a hyperplane Hx passing through X, such K is contained in one of the half places divided by Hx, then Hx is called a supported hyperplane K at X. Okay, for example, okay, if this is X, so this is Hx. Okay. So this Hx, the plane, is divided the space to 2 parts. So this is a K completely, and in here. Yeah. Okay. Someone said, okay, this is nothing. This is just the the tangent plane, but it's not true. Because this may happen to this case, may happen to this case, right? Okay. So this is not a, but if this K, the boundary is smooth, so therefore this H is is also the tangent plane. So therefore, you can see that if K is a convex set, what means a convex set? Convex sets, any 2 points in the K, the line connecting them are completely contained in K. Okay, so complex. Complex is a very strong set. If K is a convex, then for any X belong to the boundary, so there is. Oh, sorry, that should be THEIE. There is at least one support hyperplane passing through X. Okay, that exists. For convex body, it is. If not convex, okay, you can see that if not convex, okay, if it's not convex, so for any point here, right? So you cannot, you never realize this cannot exist the support hyperplane. That does not exist. So for K, the convex there is. Yeah. So therefore, if for any U is a unit vector, the distance WKU between 2 parallel support hyperplane K is called the width. K in the direction U. Okay? What this means is here. This means okay, you have this is a K convex. So this is for okay. This is U. So this is the m minus 1. Okay. And this is U, and you have okay. This is U. Okay. You have this is HX. Okay. You have the parallel, okay, here, okay. This is not H, Y, this is Y here. So therefore, this is the width, okay. This is W, U, and K, okay. This is width, okay. This is width. So therefore, this U between 2 parallel support hyperplanes is called the width of K in that direction, So when this U is, when U is changed, we have a different width, okay, the width. So if WKU for all U, this is a constant. So therefore, the K is called a set of a constant width, constant. So imagine, okay, so do you have an example for the constant width? Of course, ball, right? The ball. The ball is a constant width, okay? So therefore, the ball, BR, has a constant width to R, the ball, okay? So for example, this ball have 2. This is ball. The ball, BN, they have 2. Okay, this is a mu, this is a 1, this is a 2. Okay. So question, here's a question here. Is a ball the unique or the only set of a constant width? The question is a ball, okay? Is a unique. So intuitively, okay, we cannot find, okay? But in R2, say Reuleaux find they have the 2K plus 1 polygon, okay? Regular polygon. What do they do? So Reuleaux gives the example. Give the example in dimension 2, and the set of constant widths, which is not the disk. Okay. So what is it going to do this? Okay. So this gives us Reuleaux then 2m plus 1 gun. So this is a polygon, the pentagon. So this is a regular triangle. What do we do? Okay, you from A1, and you use it as a radial. You from A1, you draw the disk. Okay, the disk. From A2, you draw the disk. That's the disk. From A3, you draw a disk. Then this 3 disk intersection for this 3 disk, this conforms the Reuleaux triangle. This is called a Reuleaux triangle, or this is a Reuleaux and a pentagon. Okay, so this is a set of a constant width. Okay. Okay. Now I just draw this one. Okay. Okay. Yeah. Okay. So this equal. Okay. Triangle. Then you use this side. Okay. Use that. This is you draw. Okay. Okay. You get this disk. You use this one here. You use this here. You draw the disk. Okay. Disk. Okay. You draw the disk. Now you use this side. You draw the disk. This one you can draw the disk. Okay, you draw the disk. So the 3 disk, the intersection of 3 disk is this. Okay. That means you have this is a triangle plus this 3 eggs. Okay. So this is the set of a constant widths. Okay. So therefore, the width from here, this width here, this is a high, this is parallel, the parallel. So this is constant width. Okay. So this is the only one, and you can find with this way to construct. Okay. Therefore, you have the phi, the pentagon. Then you have, for any regular 2m plus 1 gun, you can use this way to get all the intersection of the disk. Okay, so this is made by Reuleaux. Okay. Okay. So therefore, you can see that for one condition, it's not enough to see if this is a set is a ball or not. So we want to add another one condition. Okay, if we add another one condition, see if you give the convex body, then this convex body could be a ball. Okay, and in differential geometry, and you put some curvature restriction, right? For the constant mean curvature or constant Gaussian curvature, then a manifold must be a sphere or ball. Okay, so therefore, what can we use another one? Okay, so if we K is in Rn, and if Vk minus 1 is constant, with the K minus 1 here means this Ki minus 1 is just the projection. Just the projection. Okay. Okay, here we put. Okay. Then you have this one here. This is the plane, hyperplane. Then you have a K here. Then you project to this hyperplane. Okay. Then you have this one. Okay. So this is K m minus 1 prime. This is K. Okay. So if this is called this volume, you have the projection, this volume. If this volume, if you can put all the direction, all the projection, if all the projection is constant, we call this, the K is constant brightness. Okay. So this is a little different from the constant width. Okay. This projection is constant. So therefore, there's a conjecture posted by Nakajima. Or any convex body in Rn with constant width, and constant brightness is a Bohr. Okay? Right? Because just constant width is not enough. Okay? So we'll put another direction. Okay? Another restriction. So in 1926, he proved, showed that any convex body in R3 in 3 dimensions with a constant width, constant brightness, and a boundary K is smooth, then it's a Bohr. Okay? So therefore, this conjecture is not solved yet. So therefore, Howard proved the conjecture for n equals 3. And that is, he showed that the C smoothness, and which Nakajima and put on, is unnecessary. Okay. So the Bohr has only convex. The Bohrs are only convex bodies of constant width and brightness. Okay. So this paper this is in 26. So therefore, they solve this conjecture, and for n equals 3. For n greater than 4 is still open. Okay. So this okay. Okay. So therefore, and just we see that constantness. So the Blaschke-Lebesgue, okay, we see compute, because we have the disk, right? The disk, and we have the Reuleaux and polygon. Okay, we construct it, and also we wish, but we have some other kind of a set of constant widths. Okay. Basic one. So they said the disk has a maximal area, and this Reuleaux triangle has a minimal area among all convex set of constant widths in a 2 dimension. Okay, so this have the area, the least area. So the disk have a maximal area. So this is looks intuitively is obvious, okay? But the proof, and it's today we say this is elementary, but it's not. It is not even far more elementary, okay? Okay. They used some I wrote the paper, and they used the convex body, and they use the flow. But to use the flow, you cannot get this one, because this is for those points you have some problem. Okay. Yeah. So therefore, later we have the Firey-Salle Theorem. The regular 2n plus 1 regular polygon has a maximum area. Okay. So for n goes to infinity, that means that go to the disk. Okay, so therefore when n is decreased, so when n equal 1, so that means have a least area. Okay, so the unique version. Okay, so 2000, and we gave the simple proof for this one. Okay, that's the proof is more easy. Okay, what do we see? We just see the 2n plus 1, and then we will see. So one of my students, and we construct of some this like this isosceles. This isosceles, we have the condition here. So we have the DC. The DC must equal the AC, and also equal to dB. Okay. Now we use this way. We from C, then we draw the arc. We draw the arc, and from D we draw the arc here. This arc, because DC equal BD. Okay. We add this to arc. We add this to arc. Then for this intersection point, we draw the arc. And from this one, we use this one. We draw the arc here. Then this one is a constant width. And also we have the 6 gang, and 8 gang, and 2n gang, and satisfy some condition. So this is the simple one. So this is the convex. This is a convex set of constant widths. Okay. So to prove this one is a convex. Also is easy, simple, not the easy, but once you construct this one, so we will compute. We compute the area of this. So what's the theta? This is the theta. Theta is the angle of this angle. Okay. So for this area is a function of this angle. So therefore, we get the area. We compute this area. Compute the area. Then we see that they take the find the maximum value or minimum value. So when theta is to pi, then this is a disk. For the theta go to the pi 3, so this go to the Reuleaux triangle. You can look at. From here you can see that means theta goes to pi. That means when A and B go to here, so this come to the disk, big disk. So when the theta, when this go to the here, so this theta go to the pi over 3. That's the Reuleaux triangle. Okay. So that's we just this we proved. Okay. So what happened in high dimension? In high dimension case, constant width. So people may think about we use a pentagon because the Reuleaux with the triangle, regular triangle, right? We use the pentagon. Okay. We use a pentagon, regular pentagon. Okay. Okay. So each of those must be equal, right? A smart student can follow the Reuleaux way to construct. Okay, you put it here. You with this the radial, you draw a ball, right? You draw a ball. Okay, so you have the ball on the side. You do this for each point. You can draw the ball. So the 4-ball intersection should be like the constant width. So this is good imagine for a smart student. Okay. So let's see what happened. Okay, like this one. Okay. Okay, you have 4-ball. Okay, you have 4-ball intersection. That's exactly like this. So this is called a Reuleaux Tetrahedron, but this is not constant width. It's not. So for three dimension, okay, intuition is not work. Okay, so we have to. So what happened? This one. So this is take a long way. Okay. Then Meissner find he gave and like shape like this. So this is constant width. He just gave. He just imagined. He gave this one. It's a constant width, and he can compute it. Okay. But so the Meissner body. So this is a Busemann-Petty conjecture. Okay, the Busemann and the Busemann-Petty in 1934, they conjectured that the three-dimensional convex body of constant width that minimize volume are exactly those Meissner bodies. The ball have a maximum volume. So this Meissner body have least volume. So this is still open. Until still open. Cannot prove. Just don't know how to, we don't know how. Okay. In two-dimensional, yes, we find many ways. Three-dimensional, no. Okay, then we think about, how about if we just concede for those rotational convex, the constant width, just like this is a Reuleaux triangle. They have the axis of symmetry. We just rotate it. Then it is. Okay, so therefore, we have the conjecture. The rotated Reuleaux triangle has the least volume among all rotational convex bodies of a constant width. Okay, for this rotated, because the ball is rotated. Okay, symmetric. If we just consider this class of rotated, okay, so therefore, they have a conjecture. This conjecture looks much easier, but it still takes a long time to do that. Only this will be solved in 1996. And Campi, Colosanti, Cronch, they proved among the class of rotational convex bodies of constant width, D, the one that minimizes volume is a rotated Reuleaux triangle. Okay, they prove the conjecture, and this is, they use some partial differential equation theory. Okay, so this is solved, and then okay, so this is the one a work we constructed the new body of a constant width and conformed and Blaschke-Lebesgue theorem and the Campi, Colosanti, Cronch theorem. Okay. Okay. Blaschke-Lebesgue theorem is two-dimensional. Okay. So this Colosanti rotated. Okay. We also constructed, and the two-dimensional case we rotated, and then we just compute the volume, computed volume. Okay. Okay. So now. And so we will see what's this something related. The something related, compute this is something related to some isoperimetric inequality. Okay, and like first we introduced before, if we have a domain, okay, and this is L, this L is the the parameter. The A is the area. So therefore, we see that only the disk, and has the maximum area among the domain with the fixed the circumperimeter. Okay. So therefore we have this, and in the high dimension case is the ball. Okay, the ball, only the ball, and for the fixed the surface area, the ball has a maximum volume. Okay, so therefore we have this inequality. So says A, that means the surface area. This omega is the unit ball. This is the unit ball, and V, that's the volume. Okay, so this is back to the from the beginning I introduced. Okay, for the measure. Okay, if you give a convex body, you give the convex body. Okay, this is not the ball. Okay, if you give the convex body. Okay, we can see the volume. Okay, see the volume. The volume. Okay, then we have the surface area. So in the calculus, we usually call this the volume. We use the volume. We see the volume, that means the volume, right? But in a geometric measure theory, we just said the volume is just the one measure for this convex body. Okay? And we also have the surface area.
Surface is n-1 dimension?
Yes, yeah. I-dimensional 1, surface area. We just forget about the volume. Everything we just said, okay, surface area. That's the one. Also the one measure, geometric measure. Okay. Then we can think about, we have many other measures. Okay? Later we will show, if we have time, we can show. This volume just some kind of projection. Okay? Some kind of projection. This surface area is also some kind of the projection to the n-1 hyperplane. Then we take the average rotation, take the average integral. So therefore, we can imagine this is just the volume, just the one measure. Then surface area is another measure. Okay? So there are two measures. Maybe some other measures. Except for these two. Okay? So those measures, we have some other measures. Okay? Other measures about for this K. Okay? So therefore, other measures we can say how many measures we have. We totally have the n plus 1 measures. Okay. Because those measures are something about the surface, the boundary of K, okay. This is the surface. The surface we have some principal curvature, n-1 principal curvature. Then we have the curvature, the principal curvature, K-1, K-n-1. Then we have something. This is K-1, we have some mean curvature, okay? The mean curvature. Some Hj, that means this m-1, this j, m-1, and some elementary symmetric function of this. Okay, this is K1, Kn-1, this is dimension. This is J symmetry. like mean curvature, Gaussian curvature, and some other curvatures. Okay, so therefore, what this means. This is isoperimetric inequality, just the equality for one measure and another measure. Okay? So therefore, this is isoperimetric, just example for some measure. Okay. Okay. So therefore, and since my time is, I just escape for this. Okay. And I escape for this. I just come to give a short. Okay. Yeah, we just gave this. This is called the core mass the Alexander Fincher. Okay. So, yeah. Okay. We just say this. We just said this is a K. This is a K, and we have projection to K to M minus R. This is a subspace. Then we have this one here. This one here, we want to compute the volume for this volume for this. Compute the volume for this. Then we get compute the volume. This is a volume. This is a volume here. For this volume, we compute this volume. This volume we must for all M minus R. All M minus R, that's Grassmannian. Okay? So we have this. So this is defined as the Minkowski Minkowski integral. This is called the WRK. So this is WRK. Okay. So therefore, we have this WI square greater than I minus 1, I plus 1. This is Alexander Fincher theorem. Okay. Then we see that all this W are equal 0 until n. So we have m plus 1 WRK. So this is what I just explained with this. Okay. So therefore, the isoperimetric inequality just one of this. One of this. So this is called the Alexander Fincher theorem, and also this is connected, medicine connected. This is connected with the global differential geometries by the mean curvature of the surface. Okay, now I give the last. I try to last. Okay. I'll give a last one. Okay, one. This is, I think maybe the many maybe interesting here. Okay. If K is a convex body, simple connected, and O is interior, then for all plane passing through O is a constant, then K is a ball. Yeah. Okay. This is a K. This is a K. And if we pass through the origin, then we get an intersection here. Intersection here. If this is a constant, you pass through constant. Okay. So therefore, this is a ball. Okay. If you take the ball, okay, you pass through the inside, the intersection is always the disk. So that's a constant. So the question is, if this is passing through is constant, if then this is a ball. This conjecture is solved by Harvard for the first one. Okay. The second one, let gamma be a closed surface enclose O. If for all plane passing through O, the length, this is R3, the length is constant, then this sigma is a sphere. Okay. So if you have the sphere, right? If you have a plane, the intersection, that's a circle. That's a circle, so that's constant. So if questions reverse, if for any surface, if you have the intersection cut, then if the curve is a constant, the length is constant, they ask if the surface is a sphere. Okay? So this one, the second one is still open. Okay? So therefore, I have to stop here. My time is up. Thank you very much.
Any questions?